In this session, we will perform quantitative analysis of a differential amplifier. The quantitative analysis means uh, we are actually finding the output. Earlier case we found what is the allowable input variation or differential input range as well as common mode input range. Here we are going to find the output as well as what is the gain of the differential amplifier in terms of common mode signal or in terms of differential mode. Actually, we are going to analyze only the differential performance of differential amplifier. Okay, so because we are more focusing on the differential gain of the amplifier. There are two methods of analyzing the differential gain of differential amplifier. One is using large signal analysis method and another one is using small signal analysis method. For any amplifier, any MOSFET amplifier or BJT amplifiers, we can derive the gain or the transconductance of the amplifier either using the large signal analysis and or using small signal analysis. As we know, the small signal analysis is more preferred because it is easy to perform the small signal analysis with the help of small signal modeling. So here also we are more focusing on small signal analysis, but in textbooks they given a large signal analysis also to find the gain of differential gain of differential amplifier. In the large signal analysis, we are finding the differential gain by evaluating the effective transconductance of the amplifier from the current equations, large signal current equations like capital ID, and then from that we are evaluating the differential gain. Now that step is somewhat purely mathematical. We need to find the value of ID1 minus ID2 or differential current due to the differential input voltage, and from that using some mathematical steps, and from that we need to find ID1 minus ID2, and from that we need to find the transconductance like delta ID by delta V in. Then using this transconductance we will find the gain of the amplifier. And most of the cases we will perform most of the amplifier circuit. If we have an amplifier circuit, differential amplifier circuit, we will find the gain or evaluate the amplifier using small signal analysis method. In differential amplifier, there are two methods to evaluate the gain of a or performing small signal analysis of differential amplifier, that are using superposition method, and second one is half circuit concept. And in this one, half circuit concept is very it's a simple method, and it have lot of applications. Most of the heavier differential amplifier circuits or differential amplifier with a different type of loads, we will evaluate using half circuit concept only. And superposition method is used to incorporate dissimilarity. So for half circuit analysis, the half circuit means we will split the circuit into two halves and then we will evaluate. So the half circuit concept will apply only if after division of the half circuit division, both the half have same property as well as the symmetry, or both half having the same properties. Okay, but in superposition method there is no limitation. Even if the transistor M1 and M2 are not identical, we can perform the analysis and we can find the actual gain of the amplifier. Okay, so first one more thing is there. If the small signal analysis of differential amplifier is a 14 mark question or essay question, then you need to perform the analysis using superposition method, because we can conclude the same gain using half circuit analysis, which required only 3 or 4 steps. But if it is an essay question, you need to perform the analysis using superposition method itself. Okay, even it is not specified, perform the analysis using superposition method. So first we will evaluate the performance using superposition method. In superposition method, as the name indicate, the performance of differential amplifier evaluated using superposition theorem. There are two input, V in 1 and V in 2. Okay, so V in 1 and V in 2. To evaluate the effect of V in 1, and V in 2, or differential in signal V in 1 minus V in 2, we evaluate the response of V in 1 and V in 2 separately. So first evaluation, we will find the response towards V in 1. At that time V in 2 will be grounded. Or in second, when we evaluate the response of V in 2, the V in 1 will be okay. And if we are trying to find the response of V in 1, V in 1 can produce output at node X as V out 1, as well as output at Y as V out 2. So we need to find V out 1 as well as V out 2 due to the input V in 1. Okay, then we need to find the difference in output V01 minus V02, and then we need to evaluate V out 1 minus V out 2 due to V in 1. Okay, so for that, first we will perform analysis. We will consider a differential amplifier with V in 2 is set to 0. This will be the circuit. Okay, so we need to perform the analysis on this circuit. So in this circuit, if we simplify or if we modify this circuit like using the concept of virtual short or virtual ground, okay, virtual ground or AC ground at terminal P, this we can neglect. Effect of this ISS we can neglect, and remaining we need to rearrange. So if we neglect that VP, effect of VP, it's look like this, and we need to also neglect the effect of output V2. V2 here we are not evaluating V2, so V2 also we need to neglect. Here it is VDD, here V in, here it is grounded, and assume that V out 2 also virtually grounded. Here it is RD, here it is RD1 and RD2. I am assuming it is RD itself. I think finally we will conclude it as RD itself, and here it is V out 1. Okay, this circuit we can redraw like this one. Okay, so for the easiness of analysis. Okay, and when we look into this one, we can see that it is a circuit where input is connected to gate, and output is taken from drain, and source is somewhat connected to ground, or in some way it is connected to ground, or it acts as a common source amplifier with some RS or something in the source, RS in source, some degradation in source. Or the circuit we can modify like this, and this will be the degradation we are observing. Degradation from RS will be the degradation from S1, the source of M1. Okay, S1. Then what is the value of RS? If RS is considering, if the V out is grounded, these two looks like same potential, or it's look like a diode connected MOS. Okay, diode connected MOS. Then the effective resistance of this one simply we can replace with its transconductance. If the transconductance of this one is 1 by Gm, the effective resistance become 1 by Gm2. So the value of RS become 1 by Gm2. So this one we can modify. This circuit we can modify like this. There is a VDD RD1 Vx, or here it is V out 1, and the M1 source of M1 is nothing but an RS. The value of RS is nothing but 1 by Gm2. Then this is nothing but a common source amplifier with RS. Then the gain is nothing but it is the gain AV we know it is V out 1 by V in 1 is minus RD divided by RS plus 1 by GM1. GM1 is the transconductance of this transistor, and the value of RS is nothing but 1 by GM2. We will get the response Vx by Vin, or V out 1 by Vin is minus RD by 1 by GM1 plus 1 by GM2 will be there. This is the first step. And second, we need to evaluate the response of V out 2 with respect to input 1. That time we will evaluate such a way that input 1 is somewhat virtually grounded. Okay, somewhat virtually grounded. To analyze that one, we need to analyze at the second half, not the first half. We need to analyze the second half. To analyzing the second half, we are neglecting the effect of this one. There is no AC variation. This is connected directly. Due to this Vin, some voltage will be here. Some voltage will be there. That some voltage we can evaluate by using the Thevenin equivalent circuit. By using the Thevenin equivalent circuit. Or I am deleting all these things. Here we are measuring voltage from this one, or this output is not there. Okay, this output is not there. We are taking output from this one. It's nothing but it acts as a voltage follower. Voltage follower, and the output at this point is nothing but it will be V in 1 itself, because it's a unity gain amplifier. Or here the equivalent circuit Vt you will get it is V in 1 itself. Okay, and what is the resistance of this one? Effective resistance that seen by M2 from here. When we are evaluating the effective resistance, we need to show all the unwanted things. So evaluating the effective resistance, so I am deleting this one, and here it is Vt is nothing but V in 1, and to evaluating the resistance from this one. Okay, so evaluating resistance, we need to short the input. Already the output is shorted, or it is grounded. Okay, input is grounded as well as the output is already grounded, because there is no effect of V out 1. So these two terminals are actually short together, or this one is also act as a diode connected configuration. For a diode connected configuration, the effective impedance of that circuit become 1 by GM1. So the value of RT is nothing but 1 by GM1. And if we evaluate this entire circuit, the gate terminal is grounded, and input is given at the source, and output is taken from the drain. So it is a common gate amplifier. It's a common gate amplifier. Using the concept of common gate amplifier, the output of V out 2 by V out 1 is nothing but RD. The gain is positive here. Please note that the gain is positive. RD by its V out 1, it is V in 1. Okay, V in 1 equal to RD by 1 by GM1 plus 1 by GM2. So this came from the gate resistance 1 by GM1, and this is due to the transconductance of M2. So by using these two gains, so these two values, Vx by V in 1 is minus RD by 1 by GM1 plus 1 by GM2, and here it is V out is RD by 1 by GM1 plus 1 by GM2. We can find the actual value such as, I think here it is V out 1, V out of 1 due to V in 1 is minus GM, sorry, V out of 1 equal to, due to V in 1 equal to minus RD by 1 by GM1 plus 1 by GM2 into V in 1. Similarly, V out of 2 due to V in 1 equal to RD by 1 by GM1 plus 1 by GM2 into V in 1. So the effective output of V out by due to V in 1 is equal to V out 1 minus V out 2 due to V in 1 is equal to, if you are assuming RD are same, RD1 and RD2 are same, it's become minus of RD by 1 by GM1 plus 1 by GM2 into 2. 2 is there because V in plus both are negative quantity. Minus is here, minus of plus quantity will be there. So it is 2 into V in 1. And similarly, we can find the response of V out 1 minus V out 2 due to V in 2. That also you will get it as the same quantity minus RD by 1 by GM1 plus 1 by GM2 into 2 V in 2. From that, we can evaluate the overall transconductance. So here it is, here we got V out 1 minus V out 2 due to V in 1 equal to minus 2 RD 1 by GM1 plus 1 by GM2 into V in 1. If these two are same, 1 by GM1 is equal to GM2, it's become minus RD by 1 by GM into V in 1 or minus GMRD into V in 1. Similarly, for input 2, V out 1 minus V out 2 into V in 2 is minus GMRD into V in 2, and subtracting these two. So V out 1 minus V out 2, which is equal to minus GMRD into V in 1 minus V in 2, and you will get the actual differential gain AD equal to V out 1 minus V out 2 divided by V in 1 minus V in 2, which is minus GMRD will be there. So you can find the gain of differential amplifier. Okay, using superposition method. So superposition method, you need to write the you need to consider individual inputs separately. For each single input, you need to evaluate each outputs using the small signal modeling or the equivalent circuit diagram. But in case of half circuit analysis, it is too simple. Okay, so here in final equation we consider both the transistors are symmetric, GM1 equal to GM2, the gain become minus GM into RD. And half circuit approach, in half circuit approach we are assuming that all the transistors are symmetric and all the resistors are identical, all the transistors are identical, and the circuit is symmetric with respect to uh, the point P. Then we can neglect the effect of point P and we can split the circuit. As per the half circuit analysis, we can split the circuit like two equal halves. As per the half circuit analysis, if there is a delta VD variation in positive part of first half and minus VD variation in the second half, the effect of both plus VD and minus VD are cancel each other, and the point P is looks like AC ground. Okay, so that point we can apply AC ground concept or the half circuit analysis, we can neglect the point P. We can split the circuit into two equal halves and the circuits look like this one. If we split this circuit into two equal halves, what we will get, this is a common source amplifier, this also a common source amplifier, and the gain is V out. So there is no coupling between first half and the second half. So V out 1 divided by V in 1 is nothing but minus GM into RD1 or RD, and here it is also same. Here it is V out 2 divided by minus V in is minus GM into RT, or in this case V out divided by V in 1 is positive GM into RT, because here the input is negative. So the V out by V in 1 is GM into RD, and subtracting these two you will get the actual output, and again you will get the same equation. The AV is nothing but Vx minus or V out 1 minus V out 2 divided by V in 1 minus V in 2, you will get is minus GM into RD itself. So half circuit analysis is very easy method. Okay, but for exam point of view, you need to perform superposition method itself. It is very important. And another method of analyzing differential amplifier, it is using large signal analysis. So we'll brief the concept of large signal analysis. In large signal analysis, we are trying to evaluate the relation between V in 1 minus V in 2 and ID1 minus ID2. From that, this will be the change in current delta ID, and this will be the change in input delta V. Okay, so from this one we will evaluate the effective transconductance, that is delta ID by delta V in, and then we will define the gain as AV equal to minus GM into RD of the differential amplifier. Okay, so here we need to find the value of delta ID or ID1 minus ID2 in terms of V in 1 minus V in 2. So how we will calculate that one? So we need to write some step to perform that one. So first step, as we discussed in the last session, we will relate V in 1 minus V in 2 in terms of VGS1 minus VGS2. So first, in this analysis, for any MOSFET differential amplifier, ID1 plus ID2 equal to ISS will be there. Okay, under any condition this will be true. ID1 plus ID2 is ISS. And to find the relation between ID1 minus ID2 in terms of V in 1 minus V in 2 or delta V in, first we will redefine delta V in terms of delta VGS. So here, for that, here also we are considering the point P. Here the point P, when we apply Kirchhoff voltage law, we can V in minus VGS1 is VP, or V in 2 minus VGS2 is VP. From that we can conclude that V in 1 minus V in 2 is VGS1 minus VP. And we already develop an equation for VGS1 and VGS2 in terms of ID using the drain current equation. There, that ID, we know ID is mu n coax W by L VGS minus VTH the whole square. From that we already developed an equation of VGS from ID. So we know VGS is nothing but root 2 ID divided by mu n cox W by L plus VT. So if we consider VGS1, here ID1 will be there, VGS2, here ID2 will be there. So VGS1 minus VGS2, we can rewritten like this. So both VT will cancel each other. So V in 1 minus V in 2, we are able to express V in 1 minus V in 2 in terms of root ID1 minus root ID2. Okay, root ID1 minus root ID2. But what we need to here it is equivalent to root some k id1 minus root k id2, and you can write it as root k into or some k into id1 minus id2 and root id1 minus root id2. We need to solve for id1 minus id2. So if we have the value of root id1 and id2 and id1 plus id2 is ISS, we can find the value of id1 minus id2 by squaring this one. If we square this one, we will get v in 1 minus v into the whole square is 2 by that common term we taken outside. 2 by is mu and cox w by l root id1 the square id1 plus id2 minus 2 root id1 id2, and this one will be ISS, right? This one will be ISS, and the equation is changes to like this one. And from this one we can find the value of id1 id2. If we are able to find the value of id1 id2, we can find the value of id1 minus id2 the whole square is nothing but id1 plus id2 the whole square minus 4 id1 id2, right? For id1 id2, using that concept we are trying to find the value of id1 and id2, root id1 id2. From that root id1 id2 we are finding id1 id2. For that we are splitting this one and taking id1 id2 separately, and we are able to find for id1 id2 in terms of ISS and v in minus v in 2. Okay, id1 here it is ISS and then v in 1 minus v in 2, and from this one we will be able to find the value of this one, that id1 minus id2 the whole square. So this one is ISS, so here itself we can convert. For id1 minus id2 is id1 plus id2 the whole square minus id1 minus id2 the whole square, or here it is ISS square minus of id1 minus id2 the whole square. So the ISS will cancel each other. We will get an equation for id1 minus id2 the whole square. So we will get id1 minus id2, and from that id1 minus id2, over here the id1 minus id2 is simply depend on delta v. So here it is delta id which is depend on delta v. So next we need to find the derivative, rate of change of delta id due to rate of change of delta v. For that we will differentiate this one, and we will get an equation like delta id like this one, and we will differentiate that one. We will get an equation like this one. If for while the differentiation we will assume that the change in input is too small, so the square term we can neglect it, and rearranging we will get the transconductance is root of mu and cox w by l into ISS, where ISS is the maximum current. So it is nothing but the normal GM of the amplifier. Okay, so you will get the transconductance is equivalent to GM itself, and we will get the gain output equal to RD into delta ID, which is RD GM into VM, or it is nothing but GM into RD will be the large signal gain also. Okay, so what we did in the small signal analysis, we perform the same in large signal analysis in a complex way using complex mathematical equations. That's all. In the next lecture we will discuss how to improve the gain of the differential amplifier, or what are the different type of loads that we can use to improve the gain of the differential amplifier.